All right, question 6. We've been waiting for this one. Determine the wavelength of the electromagnetic radiation resulting from the relaxation of an electron from an excited state, n is 5, to a lower level where n is 2, and the species is a helium plus 1 ion, so it's a single electron species. There's really nowhere to go if there's more than one electron in there. I can't really calculate much because we only can solve this for a single electron species. The moment there is more than one electron, it's really too complicated. What is the corresponding frequency and what is the energy in joules per mole of electrons relaxing? So we're asked for the frequency and then in the energy per moles. But I'm going to tell you this, regardless of whether you are being asked for the wavelength of the light emitted, the frequency of the light emitted, or even the energy, always calculate the energy. If you are using your book to consult, and that's great, you will see separate formulas for calculating wavelength, frequency, and energy. And what I'm trying to show you here, and we'll do it step by step, is I'm trying to minimize the stuff that we have to memorize, okay? Doesn't that sound good? And the only thing that we need to remember is that and the energy of a certain energy level, n, is minus z squared RH over n squared. And I think that's a simple formula to remember. So now what we're going to do is use that principle to determine the energy difference between two layers, which would be the energy released when an electron falls from a higher to a lower level. And I expect that energy value to be negative, and the negative just implies that it's leaving my system. It's leaving my system is the excited atom or the relaxing atom. Okay, so well, let's actually do this so you see how it all pans out. First of all, it's a helium plus ion, and therefore, before I forget, we'll just write down that Z is 2. And let's make sure we're clear on what is happening. So I have an N equal to 5, and lower than that N is 4, and a bit lower than that N is 3, and a lot lower than that N is 2, and much lower than that, although I want to stay in view, I have N is equal to 1. Okay? It's certainly not to scale. So the electron is relaxing from 5 to 2. So I'm going to draw the relaxation arrow from 5 all the way. Oh, I went too far. It's from 5 to 2. That's going to bug me that that's there. Hold on. I can actually get rid of that, and I'm going to. Rather than start a new video, we are going to fix that. There you go. This is like live TV, isn't it? And there we go. Perfect. Just like new. It's falling from 5 to 2. That's my electron. And I need to know what is the frequency of that radiation being emitted. Okay, so again, when it relaxes, I have this energy difference between the fifth and the second that has to be accounted for, and that's, of course, being released as energy. And it's being released as light, and light is composed of photons, and each photon, okay, has my h mu or hc over lambda amount of energy. But this formula at the moment is really not serving me, because the information that I know is that the electron started here and fell down here. And of course, this formula doesn't have anything to do with n. So what I need to do is calculate the energy of the fifth level and calculate the difference between the energy of the fifth level and the second. That energy difference is actually equal to this E. And then once I have that, I can convert it to either a frequency or a wavelength as I'm required. So that's the principle of the solution we're going to work out. So we actually want to determine what is the change in energy of this electron. And the this energy emitted is actually equal to the change. And I write that as a delta E. And the delta E is equal to the final minus the initial. So my electron started there, so I'm going to call that initial, and it ends here. This is my final. So if I could calculate, the difference, I'm going to do so by saying final minus initial. So E of the n, which I've done in the last couple of questions, but I'm going to label this as the n final, its destination level. And in this case, that would be 2. But let's just work it out all in variables and not substitute in the numbers so that we develop this general approach for any kind of question like this. Okay, that's the value of doing this question, is that you could then do any other question like it, but it doesn't have to be identical. So let's work on the approach to solving these kinds of problems. So it's final minus initial. Great. And when I find that change in energy, that's what's actually, then I'm going to say, well, that difference is actually equal to the energy of each photon coming out. Okay? So delta E is equal to, so what did I have for the energy of any n level? I've got that it's equal to a minus z squared RH over n squared. But specifically now, I'm talking about that final n squared. And then minus a negative z squared RH over n initial squared. Some of you might be tempted to take, minus a negative, that's plus a positive. Don't do that yet, okay? Just do one thing at a time. I'm substituting for E the formula that I know, minus the formula for E that I know. I see a lot of similar terms here because each of these are within the same helium atom, for which Z is 2. And so the top of both of these terms is actually a constant. So why don't I factor that out? So this delta E is equal to, let's pull out a minus Z squared RH. And then open the brackets like when we factor. And what am I left with? A 1 over n final squared, not a negative one because I took the negative with the top. Okay, so I'm left with 1 over n final squared minus, and again, if I pull out the minus z squared over RH, factor that out, I'm left with a 1 over n initial squared. So that formula looks easy enough to use, doesn't it? Let's fill in what we know. So my energy that is emitted as light, this change that in energy that occurs when it falls down, is equal to negative. What is Z? It's 2 for helium, so I have 2 squared times, I put a dot for multiplication, 2.179 times 10 to the minus 18 joules, and then that's multiplied by a 1 over its final resting place, as some students call it, the final n level where it relaxes 2, it was 2. So that's 2 squared, and I think I had forgotten to square that in class, didn't I? That's a typical error when you're just writing from line to line. 1 over 2 squared, you can write 1 over 4, it doesn't matter. And initially it started on the 5th level in this, from 5 to 2. So that's 25 or 5 squared. And I like to write it like this because I'm reminding myself as I've gone through this solution that I have remembered to square that value. Okay, punch this through your calculator. See what you get. So 1 over 4 minus 1 over 25. 1 over 25 is less than 1 over 4, so that's not going to be a negative value. So I know that I'm going to continue to have this negative sign. There we had, no, not we, it was me who saw that as, oh, that would give us a negative in class. I spoke too quickly. All right. So what did you get? Let me see what I have on my calculator. Minus 1.83. I hope you have the same answer. 1.83 times 10 to the minus 18. And this is joules. And so this is the amount of energy released, and that's why this has a negative sign. Okay, we rationalized why energy of any of these levels would be negative, but now why do I have a negative sign on the change in energy? Well, that's because it's gone from remember, this is a change, so that means that it's gone from a place of high energy to a place of lower energy. And doesn't that make sense if we say the electron is relaxing? It did, after all, change from a high energy 5 to a lower energy 2. And because each of these are negative values, right, then this comes out as a negative. So how I interpret this negative sign now as a change in energy, it means that energy is being released in this process. And I agree, because we said that the energy difference is actually released as light. That's why we've drawn it as a wavy line. It's released as light, and this is the energy of each photon of the light emitted. Right? So we can make physical sense here of all of these characteristics of our answer. So let's just write it in so you've got it for your notes. It's a negative value because, and I might ask you to rationalize why it's negative on the exam. So it's a negative value because the electron is relaxing from a higher, I wouldn't say high because we're just comparing two things, but a higher energy state, or energy level if you like, to a lower energy level. And so mathematically I am subtracting a lower energy from a larger energy, so of course the value is negative. And I would also say that the negative sign implies that the energy is released. And I think you've seen that concept in high school, where when you do a reaction and energy is released, you call it exothermic, and you determine that delta H is a negative value. You can relate that to what's going on here. The negative sign implies that energy is released from the atom. So let's make that a semicolon and say that it is released as emitted radiation, electromagnetic radiation, or light. It may not be visible, but it's all light, isn't it? Okay, and let's put, for the completion of your notes, that each photon of emitted light has an energy, or possesses that, has an energy of that value, which is what we found out, has an energy equal to, or an energy of 1.83 times 10 to the minus 18 joules. So notice how I didn't say each photon has an energy of a negative. Okay, the photon doesn't possess negative energy. The photon possesses this amount of energy. That's what it is, each photon. Okay, so one electron relaxes, one photon is emitted. Okay, it's a one-to-one, just like it's explained in the photoelectric effect. So if I have an electron So 1 electron relaxing. That results in, therefore, 1 photon emitted. All right? There you go. That's a rule we want to keep in mind. It's 1-to-1. Okay, so you know what? The question didn't even ask us for the energy, but we want to always calculate that energy. The question was asking us for the frequency. So if that's the energy of the photon, then that value that I have for delta E, what I do is I drop now the negative sign because it doesn't have any value for the energy of the photon, and that value that I just calculated is in fact the energy that I use to describe the photon, hc over lambda, or h mu. And therefore the frequency is equal to, if E is equal to h mu, then mu is equal to the energy divided by h, which is my Planck's constant. So let's fill that in. That is equal to, so I'm going to take the value of 1.83 times 10 to the minus 18 joules. Okay, so you notice I drop the negative sign, doesn't mean anything now, and I divide it by Planck's constant, 6.626, there we go, times 10 to the minus 34 joule seconds. And I can see that those will cancel, and I'm left with seconds on the denominator, so it'll have units of seconds to the minus 1. That frequency is, hold on. Oh, I didn't actually calculate it yet. Okay, I'll put it in the calculator. So you can do the same, 1.83 exponent 18 minus, that's how it goes in on my calculator, divided by 6.626 exponent 34 minus equals 2.76 times 10 to the positive 15, that's seconds to the minus 1, or hertz if you like. So that's the frequency of the radiation. And I think that on this we were asked for, oh, we were asked for the wavelength as well. Actually, we were asked for that first, but it doesn't matter. Wavelength. E is equal to hc over lambda, which is also equal to h mu. So there's two ways that I could find the wavelength. I could take my, I could say that wavelength is equal to hc over E, but now that I actually determine the frequency, and I know that frequency is c over lambda, and I just found frequency, why don't I use the simpler formula and say that therefore lambda is equal to c over frequency. Okay, really squeezing this on the page here. So I've got my speed of light, 2.998 times 10 to the 8 meters per second, and that is over my frequency, which was 2.76 times 10 to the 15 seconds to the minus 1, and I will get my wavelength in, I'm just looking at the question, it didn't ask us for any specific unit, so I'm going to leave it in meters. Okay, calculator back, 2.998 exponent 8 divided by 2.76 exponent 15. And I get 1.08 times 10 to the minus 7. 1.08 times 10 to the minus 7 meters. There's the wavelength. Let's check back at the question, the original question 6. What's the wavelength? What's the corresponding frequency? And what is the energy in joules per mole? Okay, so we did the frequency. Boom, we've got the wavelength right here. And they wanted also to know the energy. So we found the energy, but in fact it was the first step on the way to wavelength and frequency, even though they didn't ask for that in that order. We have to do that first. So back here, if I multiply this by Avogadro's number, I will get 1.10 times 10 to the 6 joules per mole of photons emitted. So let me just squeeze that in over here. Okay, let me go this way with it. How much energy per mole? That would be 1.89 times 10 to the minus 18 joules, and multiply it by Avogadro's number, which I'm just going to symbolize as Na. And the solution is 1.10 times 10 to the 6 joules per mole of electrons relaxing. Okay, 1.10 times 10 to the 6 joules per mole of electrons relaxing. So I have that many moles of electrons relaxing, I have that many moles of photons emitted. So I could have written that this is the amount of energy per moles of electrons relaxing, or I could also write this much energy per mole of photons emitted. You might be wondering, what happened to the negative sign? Again, that negative sign just says that it's emitted. So I can leave the negative sign on there, or I can just say that it is being emitted, the photons, and that takes care of it. Okay? This is a really, really important question. Question 5, what was this? Sorry, no, not 5. This is 6. Question 6, question 7, and question 8 that you turned in as an assignment are really important questions. Go over this. Any question that you have surrounding its solution that we've just done, do not hesitate to ask me. Ask me in class, ask me in an email, whatever your mode, preferred mode. Important thing is ask before the exam.